test flights by both MSN-1 and MSN-3.
Okay, so welcome on board. This is the A350 XWB. XWB stands for extra wide body because it's got a wider fuselage than our previous aircraft. When you walk on board this aircraft, there's a couple of things that you notice. First of all, you notice that there's no panels, there's no cabin really, okay? And the second thing is you notice a lot of orange. Everything that you see in orange is flight test instrumentation. It's the code color for it. So all of these racks, for example, those would not be on a regular aircraft. Everything else would be on a regular aircraft, but would be covered. So you see the hydraulic, the pneumatic ducts. You see that there's a lot that goes on behind what we can actually see. Okay, and then on top of that, everything I said that's orange is flight test instrumentation. We have 41 tons of flight test instrumentation on this aircraft. It's the aircraft that's the most heavily instrumented, and it's because it's the aircraft on which we do the performance testing. So low speed, high speed performance, it's done with this aircraft. We have 600,000 parameters which we pick up and which we measure, which we study. You'll see in the back there's a massive amounts of computing power to process all that data. Anybody want to guess if you took the flight test instrumentation, lined it up side by side, how long the cable would be? Wild guess? 5 kilometers. 400 kilometers.
Wow.
It's really impressive how much instrumentation there is.
Is the A350 a fly-by-wire system?
Yes, okay. All Airbus aircraft are. Yeah, everything is. So, in the performance campaign, there's a lot of tests that we do. In terms of low-speed performance, one of the tests that this very aircraft did recently was high-altitude takeoffs. When you take off at higher altitudes or at higher temperature, the air density drops. When the air density drops, the performance out of the engines, the thrust, is basically reduced. So it's important to go test the aircraft at these conditions. So we took the 350 to La Paz in Bolivia. The airport is at 14,000 feet. So we did a lot of takeoffs out of that condition. We did some cold weather testing. We cold soaked the aircraft in Canada, minus 28 Celsius overnight, and then we see how the systems react the next day. Another really impressive test which this aircraft did was the VMU, velocity minimum unstick. It's basically to test how slow or what is the minimum speed at which in high lift configuration the aircraft will take off. Okay, so it's basically one of the tests where the aircraft scratches the ground as it's taken off. It's very impressive. If we talk a little bit about the aircraft, it's the highest content composite commercial aircraft. So you don't really see it because of the lining, but everything, the floors, the walls are all made out of composite material. And that contributes to dropping the weight of the aircraft quite substantially. If you look at a route like Singapore to London, 6,500 nautical miles, you compare it to a 777-300ER, so same size, same capacity, you have about 20 tons less in terms of structure. And on a route like Singapore-London, you have 20 tons less fuel because you're not going to consume as much fuel. So you have 40 tons less at takeoff. So very, very efficient aircraft. It'll burn about 25% less fuel. And that's very important to airlines because half the cash operating cost is fuel. So what you're looking at right here is the flight test engineers, well, the station basically. They can see the aircraft in a level of detail that is quite impressive. They have more information obviously than the pilots. They can see in terms of hydraulics, electrical networks, they see really the aircraft in a really impressive manner. They of course cannot fly the aircraft, that's done from the front, but they do see quite a lot of data. Now there's a third flight test engineer, which is on most or on some flights, it's the Rolls-Royce station. As you know, our engines are Rolls-Royce. Trent XWB, highly efficient engines, the world's most efficient engine flying today. And so he's here, and he has access basically to engine parameters. These guys also have access to engine parameters, but he has a higher level of detail. And what's quite important is that he can also play with the schedules in the engine. So the VIGV schedule, which is basically the inlet guide lanes, the fuel schedule. So you can treat in terms of performance. And we've also done tests where we stall the engine, we surge the engine, or where we do a flame out. So he's the one who's capable of controlling that from the station right here. The corridor we walked through, that's basically the bays where where the data is recorded, exactly, the data position systems. What you see in front of us right here, there's a couple of other ones in the front of the aircraft. These are basically electric loads. Since there's not 315 passengers using their IFE, there's no flight attendants using the ovens and the galleys, the aircraft would not be loaded electrically the same way. So what we need to do is to simulate full electric load. So all these things actually do is just drain electricity from the aircraft. That means that we're then going to load the engines mechanically, because the VFGs, the variable frequency generators, which create the electricity, are basically powered by the engines, by a drive shaft coming from the engine. So that's what these do. The seats are, I mean, it's not A350 standard seats. An airline wouldn't have something like this. These are seats for the flight crew, the mechanics that travel with the aircraft, the crew. So we have about 50 seats in there for that. And when we don't have the seats, we can put water ballasts, and there are some as well on the cargo deck below us. Yeah. So the water ballast is exactly to simulate the weight. So, for example, the max takeoff weight of this aircraft is 268 tons. That's the weight of the aircraft plus the fuel plus the passengers, the whole payload. So, in order to simulate that, to see how the aircraft takes off at max load, we have these water ballasts that we can fill up. What we can also do is move the water from tank to tank to move the center of gravity forward and back. This has an influence as well on the performance of the aircraft. There's a total of 5 test aircraft. 2 of them are flying. This is the second one to have flown in October. 2 more are going to come online in the next coming days. And the 5th one is a bit later on this spring. So we've got a total of 2,500 flight hours planned. We've done about 1,000, so we're a bit more than a third of the way there. A lot of flying. The aircraft flies sometimes even twice a day. It's going to fly from here after the display straight to Toulouse. That's about a 13.5-hour flight, if I'm not mistaken, with the winds, depending on the winds today. So it's gaining a lot of experience, gathering a lot of data, and it's on track to enter service on time, which, you know, is something that's we get more and more skeptical of people because of the delays in the past with some of the aircraft, and the A350 is really on track. A lot of maturity, a lot of testing has been done upstream of the flight test, so we've really got a lot of, if you will, knowledge or experience, maturity into this aircraft family.
Will these test aircraft be eventually delivered to airlines? Or?
Some of them will. This one probably not, because of the level of instrumentation. We keep our flight test aircraft. So we have 2 A380, for example, flight test aircraft. We have an A330. We have an A340 as well. We continue to test different systems. We continue to drive further innovations on the aircraft with these flight test aircraft.